Cool. Yeah, thanks, Sydney, for the nice introduction. This is the third time I think I give this State of Containers talk. And I will start with a little recap on the technology, and I hope to make this piece of the talk shorter and shorter over time, so because everyone is like adopting containers and it becomes common knowledge, so I hope that I can squeeze it a little bit. And then I will just start a discussion or like give my thoughts or our thoughts, how we want to embrace HPC and big data with containers. And at the end, there's a little outlook. So first, a short recap on the container technology, and the most interesting and the most fundamental part is namespaces. So when you look at the container technology over time, it starts with change root, and I stole this chart from a talk at KubeCon, but I think it's nice because it elaborates on what was the different milestones we had so far in terms of container technology. So C groups, namespaces were introduced in 2006, but before we all were also build on top of or stand on the shoulders of giants, right? And in 2008, LXC brought it into the public space a little bit, but it was still a kind of a virtual machine setup using container technology. And then in 2013, as we all know, Docker made it a public or a more easy usable system so that everyone can use containers. And that's where we are now. And as Sydney said, I joined Docker like 5 months ago. Feels like 5 years, but that's a different story, I think. Iterate on namespaces a little bit. Namespaces are just a means to isolate process groups or C groups. And the most easy one to understand is the PID namespace. So if you have containers running on a host, they can only see the processes that are associated with this container. So if I do this command, for instance, I do docker run and I do ps-ef, I will only see my little ps-ef process, and it will get the process ID 1, because it's the first process in this namespace. Same as your init system will have the process ID 1 on a normal system. And this is only the view of the container, right? So if you create a container with a sleep command, for instance, and then you look at the process table from a host perspective, this is what the second command there is, it will show you the process ID of the host. So in this case, the sleep command has external of the container, it has the process ID 9670, but within the container, it thinks that the process ID is 1, because the resource table, which is the namespace, will have a new resource table for all the different namespaces. So in this part, it's 9670 on the host, but in the kernel, in the container, it's 1. And there are a lot of namespaces out there. Currently, there are 7, so I won't go into all the details, but they are basically just providing the resources that are created for each container individually. And there are others proposed. One is syslog and time. Like time would be a fun one, so that you have different times in different containers. It will be a weird one, I think. But Mellanox introduced RDMA into the kernel. It was not picked up so far, but I hope that this will be picked up soonish, so that we can use InfiniBand native and managed by the kernel. I think that would be nice. But yeah, there are different namespaces, and hopefully we will iterate on ones that are good and easy to use for HPC as well. So namespaces, as I said, there's in the kernel, and the host has its own namespaces that are provided for the host itself. And if you start a container, then you will create all the namespaces for each container that you start. And this feels like virtual machines, even though it's not, but it feels like a virtual machine. If you log into one container, you cannot see all the other containers, so it feels you have an isolated guest, so you have an isolated container. But where this analogy breaks a little bit is when you share namespaces between containers. So for instance, you can share the namespace of the host, the network namespace in this case of the host, and then your container will have the same network interface, it will have the same host name, it will have the same IP addresses as the host has. So there it breaks this analogy. And also you can have a container using or reusing the namespace of another container, which is heavily used in Kubernetes. And so you can have the same IP address and you can talk over localhost or over shared memory with the IPC namespace, so that it feels as if the containers are on the same host. And a little scary one that I did last year as well is you can join all the host namespaces, except mount and cgroups, but that's another story. But if you run this command, you can log into the host that the Docker engine is running on, and then you change root into the host file system, and then it feels like as if you logged in via SSH. So this is also where the notion of virtual machines or the analogy breaks a little bit, because you cannot do this with virtual machines, obviously. So that's SSH root at Docker host if you run this. Okay, so this is namespaces, and namespaces are only isolate containers or process groups for that matter. So if you run a container that uses the stress command that we all know, and you run it only this container, then it will be able to allocate or consume all the resources of the host. And you can constrain this resource allocation via cgroups. And in this example here, I first pin both containers only on the first core of my laptop, because I don't want to burn it when I run stress. So I pin it on the CPU core 0, and I also provide a number for CPU shares. So and you can see it here on the screencast, the first container will consume 100% of one core, because I pinned it to one core, it will only use one core, so it's 100%. And if I start the second one, then due to the different CPU shares here, the upper one is 200, the lower one is 100, it will consume 2/3 and 1/3 of the host, of the CPU that is assigned to both containers. So with control groups, you can constrain resource consumption, whereas with namespaces, you isolate. So with cgroups, you can constrain the resource consumption. I think which is a nice thing to do, I think, for if you have a Bitcoin miner, for instance, and you want to run it when nothing else is running, you could use this technology or this CPU shares to only let it run when nothing else is running, or maybe not Bitcoin miner, but something else. I mean, you guys, I think, have use cases for that. Okay, so we have namespaces and cgroups, and another thing that was introduced or popularized by Docker is overlaying file systems in context of containers. So I use my Ubuntu image here, and when I want to install something, and in this case I want to install OpenGRE, I just use the from command to inherit whatever the Ubuntu image is providing me, and then I install OpenGRE in the container. And on top of that, I can install an application. Let's say I have app.a.jar, and I want to install it into the container. I build on top of the intermediate image OpenGRE, and then I copy the application in, and I provide a command how to run it. And this will provide me with the proper container to run app.a. And if I want to change the application to app.b, I can piggyback on the previously created OpenGRE container or image, and then I have another application. And in this case, we have only 4 layers, right? I don't have to copy the complete thing for the second container. I just piggyback on what was provided for app.a. Imagine that there is a new version of OpenGRE out. If I'm smart with my Docker files here, I can even create another OpenGRE image and then rebuild app.a and app.b and have multiple versions of the applications with different underlying libraries. And in your case, I mean, you can imagine that you have OpenMPI or MPI from DK Panda or different other libraries, and you can create a tree of different permutations of configurations, libraries, that you can piggyback on for your application. So you can have a vast set of libraries, and you don't need the shared folder for all the binaries and libraries, but you can version it with this approach so that you can just say, okay, this is my container, and everyone has the same container. And you can use this content hash of the container to make sure that you run, or every one of you run the same container. I think that's also very, very cool. Okay, so now I want just to quickly contrast traditional virtual versus container virtualization. And I showed this slide a couple of times. So with traditional virtualization, we have the host kernel and the user land of the operating system. And within the operating system, I installed VirtualBox, for instance, so a type 2 hypervisor here, which runs next to a couple of other services. And this hypervisor will emulate guests, which I can use to install other operating systems. For instance, now I have container 1, or VM1 and VM2, and they can have like CentOS, and the other one can have Ubuntu, so you have distinct operating systems distinct guests for distinct purposes. But you still have the overhead of this hypervisor in between, right? There are some nice tricks and some virtual machine shortcuts to make it a little bit faster, so you can pass in a PCI device, which you can use with SRIOV to provide a virtual function to a specific virtual machine, and there are other techniques to make it faster, but you still have this hypervisor in between. And with containers, with OS virtualization, it's very much so that you run on the host kernel and you only have one kernel to communicate with, and the host kernel is in charge of all the processes on the host. Whereas if you use VirtualBox, for instance, if you supply it with 4 or with 8 or whatever CPUs, it will create threads on top of the host kernel or within the operating system, and it doesn't know about the NUMA layout of the host, for instance. So with this approach, the host is aware of all the applications and all the binaries running, so he can make smart decisions in terms of a NUMA layout, for instance. And then you have container 1 and container 2. A different view is the interface view. So if you have an application that is either statically compiled, so you have only syscalls, or you have a library that then translates it to syscalls. With the traditional virtualization, you talk to your kernel of the virtual machine, and this kernel then will talk to the hypervisor underneath. In this case, I choose a type 1 hypervisor, so you don't have an operating system or a distinct operating system, but it's baked into the hypervisor itself. And by doing so, you utilize the 300 or 350 or how many syscalls we have now in Linux, and the hypervisor uses hypercalls, and these hypercalls are 30 or 40 that are used to communicate with the hypervisor, and the hypervisor then talks to the underlying hardware. And if you use containers, you just have this very simplified view. So you have the application that might use libraries, and you bundle this up in an overlaying file system, and this is then instantiated as a container, so you don't have any overhead using a hypervisor. And this provides you with a very nice and easy abstraction. Okay, but how can we use all these technologies to actually use containers or create containers? And the Docker architecture looks like this, and I won't go into the details, but at the bottom we see the operating system, which provides us with control groups, namespaces, and so on. And we utilize runc as a runtime and containerd as a very small wrapper around the runtime to create and start containers. And the Docker engine has a lot of different pieces to ensure that you can pull containers, that you can push containers, that you have a little orchestration tool, Docker Compose, and so on. So it provides you with a tool or binary or a runtime or a Docker engine to just use containers as easy as like Docker LS and so on. So you can just easily integrate it into your workflow. And we will see this in the little Twilight tutorial I put together in the evening, like 5:30, I think. And just to show you how that looks on Windows, it looks like kind of similar, which is surprising, or at least to me it was a little surprising that Windows, with the latest version of Windows, they created the equivalent of control groups and namespaces. So, and they put a little service on top so that our Docker engine can talk to the Windows server and create Windows containers that are native on top of the Windows 2006 server system. So you can start a container that runs Windows inside, and it talks to the underlying kernel of the Windows host. So you don't need to have virtualization like traditional virtualization, hypervisor virtualization in between. So not only do we run on Linux and Z-Linux, but we also run on Windows now. So if you have pre- or post-processing stuff that you want to do, you might be able to just put it in a box and put it on the operating system with Windows. On top of that, we provide the Docker Enterprise Edition platform, which is the engine itself that I just described, but also it has a single pane of glass to manage and monitor your cluster, which is the universal control plane. It has built-in security and access control and another couple of other options so that you can rely on your LDAP or Active Directory. You can assign roles and grants, so very fine granular, so you can only allow an administrator, for instance, to kill a container, but the engineer is not able to do so. He can maybe just start on a couple of nodes. So we have this RBAC. And what we also provide with the platform is a Docker Trusted Registry, which is an enterprise-grade registry which you can use that hooks into Universal Control Plane to have also RBAC and LDAP integration. You can scan your images with regards to CVEs. You can also use this as a rule to promote images. So if someone pushes an image, then it's scanned. If there's no threat, like no bash exploit or something, then it will be promoted to some repository that everyone can use. And you can also use this promotion to check for licenses. So if you say, I don't want to run GPL-v3 license containers, then you can create a rule that only allows promotion with regards to the license used. And it could be a central registry for all your environments globally. And we can mirror different DTRs across different environments. So you can push and pull and share your images with other universities or facilities. And we have a very, very big ecosystem around it. So, I mean, Docker is now 2 years old or 3 years old, the company. And we partnered with a lot of other companies to provide certified images and to provide an ecosystem which you can utilize to maybe enhance your operations using monitoring or logging or inventory. And this is just Shard to elaborate on that. And I hope to see a lot of HPC companies to be added to this in 2018 so that we can provide everyone with a nice ecosystem for running HPC and big data workloads. Okay, so this is just a wrap-up of what containers are and what we provide. And now I would like to have a little outlook on what I think we should do, and with a collaboration effort to make the Docker engine so that everyone in HPC and big data world can use it. So the problem is that, or not a problem, but the focus so far is that the Docker engine is very host agnostic, because we used to be more in the cloud space of things. The Docker engine is the same for all the different nodes, and it does not have host-specific configurations that you can apply. So if you have, for instance, a GPU, and you need a different CUDA on different hosts, you need to make sure that this is somehow mapped into the container. And this configuration is a little bit cumbersome as of today because we don't provide host-specific configurations for starting container. So what we need to do, and I push for this internally, that we make it so that the host 1 and host 2 can have different configurations so that different devices or different volumes are mapped into each container if you provide it with a flag or a label or whatever. And this, I think, is it's easy to do. I mean, I did it with a little Go program I hacked together. It's pretty simple because we just need to change the payload of the Docker run command, basically. So it's not very difficult, but we need to find out where to put it. And this is just a simple example of generic GPU usage, so mapping in the driver and mapping in the device, and then you can run, and it is like here on the bottom right, you can run Docker Compose up, and it will create 2 containers here. One is a CUDA container, which is like built on the left-hand side, and the other one is just an image of Ubuntu that maps in the volumes of the first container, so all the libraries. And it has no notion of the NVIDIA binaries and libraries, but it maps in the volume from the upper container, and so it can run NVIDIA SMI and list all the devices that are able or available for this host or for this container. And this can be scaled to multiple GPUs as well. I just fixed the Docker Compose file a little bit to have different containers in the same manner as on the previous slide, and map in different devices to the different containers. And what you see here on the right-hand side is that every container thinks that it has a couple of GPUs. And and a couple of the upper 2 are shared, right? So you see the ID that's the same. So they are shared. So it's not multi-tenant ready because you can access each other's memory regions. But this should be the first step to have single tenant GPU access available for containers and make it transparent so that you can use a little label in your Docker image. And when you start the container, it will be mapped. Or the devices and drivers will be mapped into the container without the user doing anything. And I think that's the first step we need to take. Another thing that's also very important is to honor shared environments. As you all know, you don't want to have one user post as a different user and access the home, for instance, or access the projects and Scratch file system as a different user. So what we need to do, and it's also not hard, and I have it on the second slide, or one slide afterwards, we need to enforce the user ID of the user that is calling the container. So in this little example, I'm Charlie, I run a container mapping in the home file system, and I want to be Alice. So I say ---- user, and I use the UID and the group ID of Alice, and when I touch some file in the home directory of Alice, it's as if Alice would have put the file there, right? So this is dangerous, right? But it works as designed, because we are host agnostic. We don't, or our best practice is to do not trust the user ID within the container anyhow. So that works as designed. And what I did with a little simple Go library or Go program here, I create another Docker socket, which is then used to create the exact same container as before. And I try to post as Alice. But my little proxy checks for this user flag and overrides it with something that I can provide or that I can get from the calling command of the Docker CLI. So I can override the user to be Charlie. And then Charlie cannot access the home of Alice anymore. So it's just a safe gate or a gatekeeper to just override the user flag and make sure that if you're trying to start a container, it makes sure that you are the user that you are supposed to be. And this could be used, you can use like Slurm job user, for instance, to make this a thing. And it doesn't matter that the authentication provider within the container doesn't know about the user ID. So if you do who am I within this container, it will tell you, I don't know. But you have the user ID of Bob or of Alice or Charlie, and it will put files that are outputted by this binary, just as if you would run the library or the binary as a user on the host directly. So those are the two things I would like to push for in the upcoming months. And another thing on top of that is, if once we have done this, we can make Docker engines and HPC workload schedulers work together. As of today, as you all know, the Docker engine on the left-hand side is just what I described, right? We create containers that are not shared system aware. And on the right-hand side, we have the HPC workload scheduler like Slurm. And it will create processes on behalf of the user that scheduled the job. And it will create the processes within the shared environment, the shared system. And what I would like to see in the upcoming months is that the Docker engine underpins both workloads, so that we can run, as we do for forever, containers just as we did it before, like process 1, process 2 are just simple containers that are not relying on a shared system, but that we can also then create containers that are aware of the shared environment, so that we can use GPUs and we make sure that a user is not able to override or remove files of another user by enforcing the user ID. And once we've done this, we can underpin everything, and we can underpin Kubernetes workloads, Swarm workloads, or HPC workloads with one Docker engine. 4 minutes. Oh, Sydney. OK. And by doing so, we are able, as said, we are able to combine different workloads and different approaches. And as DK and others showed, nowadays it's not about HPC anymore, not about MPIs anymore. We have MPI, machine learning, deep learning, and everything has to come together. And I speed up my talk. Everything has to come together and be combined to be used in the multidisciplinary world we are living in. So with this, you can utilize whatever comes out of the Kubernetes ecosystem or the Swarm ecosystem, and you can just use it and combine it with different workloads. And these are the tentative milestones I put on me, basically. The first milestone is to do what I just described, like have transparent support for kernel bypassing devices like GPUs and interconnects and InfiniBand, and also have secure operations in shared environments, in particular by pinning and forcing the user, so that you are not able to access other user data. And then the second milestone towards the middle or the end of the year is to integrate workload schedulers, so that you can use Slurm, for instance, and Slurm will natively create containers as I think is best, or we think is best. And but that we will see, I think, later in the year. To foster this, I teamed up with the student cluster competition team of Hamburg, and our goal is to first foster containerized auxiliary services, and I gave this talk about auxiliary services last year. So for monitoring, logging, and such, that you can create environments where you can easily debug your system by using containered services, and also as a second goal, stretch goal, to prototype the workflow that I just described and the integration that I just described. And these are the touch points in 2018. Everyone, or most of you guys hopefully will join this. We are now kicking off this initiative a little bit. Then in April in Lugano, I will be presenting, and it's not, don't have an agenda yet, but I hope I'm allowed to present the progress that we made. As said, in June, we have the DockerCon where I will talk about HPC as well, but more important for you guys maybe is the ISC, so I will talk about GPU integration, shared environments. And also we have the student cluster competition there. And obviously at the SC in Dallas this year, we will also target to talk about HPC. And hopefully some other student cluster competition member of the SC18 can join and can use Docker. And if you want to be coached, then approach me or Christine and we will make it happen. And this is my last slide, I think, the call for action. So how you can get involved and how you can help me, that would be nice. 2 years ago or 3 years ago, you guys reached out to Docker to help you push containers in HPC and big data. And as said, we were more focusing on the cloud guys, so it was not on the agenda. But now I'm reaching out back. I mean, it's 3 years late maybe, but we try to make HPC and big data use cases a thing within containers. And as said, it's very simple to do so, but we need some momentum. So if you are already a customer of ours, ask your contact for HPC and big data use cases. And if you're not, then maybe even better become one and then push for HPC and big data use cases. And so we can gather the critical mass needed to adopt this within our environment. And to prepare for the adoption, use Docker, obviously. That's an easy sales pitch, right? But maybe create a center of excellence that we heard from Adam. So create a COE that uses containers for maybe development purposes first, and that you are ready to adopt containers once we finish up the milestones that I provided before. Yeah, and if you push this internally, or if you push it towards Docker, then I will gain more and more momentum to make this a thing. And this is my last slide. Containers are a goldmine anyhow. I mean, you can sign images, you can bundle up the apps and libs as a recipe, as a Docker file, and you can optimize. And this is something I would really like to see, that we will look into this more and more. Optimize the user land to best support only the application, right? So in a container, you don't need to care about systemd or syslog or whatever. You don't need to care about the operating system services that you normally have to care about. With this, you can just focus on your application and tweak the user land as you please. And there are other stuff that we will talk about in 2018. I'll just keep it here. Okay, cool. Thanks. That would be it. I just leave this slide there for the workshop. If you want to look the slides, sneak peek on the slides, it's a link. And you should download Docker for Mac or Docker for Windows to participate. Yeah. And I will take maybe one question. If not, Sydney looks suspicious. But I will be around today and tomorrow, so if you want to chat, then please feel free. All right, thanks.